factor theorem, which I've already laid out for you. The factor theorem is basically if the remainder is 0, you have a factor. There it is. So this is now going to be useful for us to take a cubic, a quartic, a quintic polynomial and be able to factor it. Because now we're going to be able to find a factor using the factor theorem, synthetically divide it out, and keep going until we have a quadratic. So remember how I said you're going to learn how to factor these higher degree terms? This is that last piece of that skill. So let's do it. Let's divide this polynomial by x minus 5. Now again, we've done this already, but we're in the quarter system. I'm going to use synthetic division and do a division. So I'm going to divide by 5. Quick reminder there. We take the roots, so we're allowed to add. 1, -6, 3, 10. Synthetic division is drop, multiply, add. Multiply, add, multiply, add. That last value that you find is the remainder, and then each column is an increasing degree of x as I move back towards the root. So I would be able to say the result of the division, the quotient is x squared minus x minus 2, remainder of 0. Now that it's a quadratic, could I factor that quadratic with all the other skills that I have? Yeah, so now I've taken a cubic, I've divided out my x minus 5, and I would be able to factor my remaining to be able to have all of my x-intercepts. So use the remainder theorem to verify your remainder. Remainder theorem basically says, take the polynomial, plug in the root of your divisor, put it into your equation, oh, I put it at 0 for some reason. 5. Calculate it out. Okay, let's see here. 125 minus, that would be 150, so that'd be -25, plus 15 is -10, plus 10 is 0, but I knew it was 0, I just, I like math. So I proved it, I got the same remainder. What does this tell you about x minus 5? So this is that link. We know that is the statement that I can now make. The polynomial at 5 has a value of 0, which means I have the point 5, 0, which means that I have an x-intercept. I can also now interpret that I am going to have this as a factor of that polynomial. It's a root, it's a 0, it's a solution. So all of these words are going to be used in different contexts, depending on what you're being asked to do. So write the factor the quotient and write the polynomial in factored form. Well, here was my quotient. We're able to factor that nicely, so that's just going to be x minus 2, x plus 1, which lets me give the polynomial. So remember, we're going back to the beginning. I like to think to myself, if this is a cubic, I should have 3 factors in this case. The first factor that worked was when I divided out x minus 5. When I factored the rest of the quotient, I had x minus 2, x plus 1. That is the factored form of that original cubic polynomial. And a quick check to see if you dropped something. Make sure the degree of your factored form is the same as the degree of your original form. So guys, basically, degree 3. Leading coefficient is positive. What do I now know about a leading coefficient positive? Degree 3. Well, all of my odd degrees behave like a line, right? So that means I would start in quadrant 3 and end in quadrant 1. I'm taking this opportunity to do a little review from yesterday so we don't forget all of this stuff. So degree 3, positive leading coefficient, I know the start and end quadrants. The factored form gives us the x-intercepts. My original form would have given me the y-intercept, which is 10. And then guess what we're ultimately going to be doing? Oh, that's terrible. I didn't even go through 2. Let's try that again. Ultimately, guys, this is where we're going. You pretty much have most of the information. You don't have it all yet, but you've got a lot of it. So do you see how that's coming together slowly? All right. So the factor theorem basically states for any polynomial x, the polynomial at a value, if a polynomial at a value is equal to 0, then x minus that value is a factor. If that polynomial at negative a is equal to 0, then x plus a is a factor. So basically understanding you're using a root, and you have to do that opposite sign. If x minus a is a factor, then the polynomial is equal to 0 according to the factor theorem. Baby step, like I said. This is not a huge, huge theorem. So, and if x plus a is a factor, then the polynomial at negative a is equal to 0. So now we just use the factor theorem to show that a particular divisor is a factor. If the divisor is a factor, the remainder is equal to 0. All we're going to do is plug in the root of the divisor into my polynomial. One minus 6 is negative 7. Negative 7, 1 minus 6 is, let's try that again, is negative 5, plus 11 is 6, minus 6 is 0. That's all you need to do to prove it. Fair enough? Does that make sense? Do we have any questions about that? Okay, so now we kind of say, which of these are factors? It's just a matter of using that remainder theorem over and over and over again. Now, I'm going to show you a little calculator trick here. I like to calculate in my head, but again, I like to take the opportunity to show you a few calculator tricks. So, would you agree with me that I am going to be plugging in a different root into the same equation 4 times? Okay, knowledge allows you to take shortcuts. So this is what I'm going to do. I'm going to write on the board so that I don't forget, because the older I get, the worse my memory is. I'm going to do this. I'm going to say, you know what, guys? I'm testing negative 1. I put that in as an answer. Then I'm going to write the equation as the answer cubed for my x minus 6 times the answer squared plus 11 times the answer minus 6. And of course, as we know, it's taking the last answer it calculated. So this is going to save me having to write this out 4 different times. So I hit enter. Is x plus 1 a factor? No, because it does not equal 0. Was it positive or negative? Good. So not a factor. And I don't need to see what you plugged into the calculator, by the way, guys. I mean, like, we're starting to evolve beyond that. So now I want to check the value of the polynomial at 2. So, calculator trick, 2 is now, oh, I'm holding a pen. All right, 2 is now the value, and I'm just going to pull up the equation again. and then I can hit enter, and it'll put 2 into everywhere I see the word answer. So instead of me retyping it over and over again, this is kind of a little shortcut. So I got a remainder of 0. What does that tell me? It is a factor. You are the father. Did anybody ever watch Maury Povich? Yeah. So you are a factor. It is a factor. Then we keep going. We evaluate at -5, and we evaluate at 3. And because I have that all typed in, I put in my value, hit enter, go second function, enter twice, and let it do its work. So I get -336. So you are not a factor. One more time for 3. I get 0. You are a factor. Was there a quicker way for me to do that? Yeah, could I have just looked at the table of values? Could I have just stuck that into my graphing calculator, looked at the table of values, and found out where all of those values were? Yes. I'm showing you that technique because sometimes when you do repeated calculations, and it will happen, it's a nice little thing to know. But there's a whole bunch of ways you can do these problems. Graphing calculators do have some advantages. Still not a big fan, but I can see their usage. But another way, put this into your equation, go to your table of values, look at the points for x. Put this into your y equals, graph it, and find out where they are. Would that have all done the same thing? Because I really want you guys to associate. Those are all just points on the graph. All right. So, in general, the factor property. If x minus a is a factor of the polynomial, then a must be a factor of the constant term of f of x. I actually call this the integral 0, 0, which basically means I look at the constant to decide which values I am going to try to find as a factor. Now, this is Rollick. I'm just going to use my graphing calculator. Great. What happens next quarter when you're with me in calculus and you don't have your graphing calculator? So again, I need you to understand I've got 2 purposes here, right? I need you to get the math so when I remove your graphing calculator, you can still do it. But because you've got the graphing calculator, you can do it in an easier way. So do you see how I've kind of got 2 things I'm trying to accomplish? So I'm trying to do both, and you might go, she's always making it harder. It's because I know that I'm going to be removing something from it. So basically what it says is, if this is my polynomial, and you don't have your graphing calculator, you're in calculus, and you do have to factor these things in calculus, you would say, all right, my constant is -3. Therefore, my potential zeros are the factors of -3. I am going to seek the value of the polynomial at positive -1 and at positive and -3. I don't care about 2 because 2 is not a factor. So once I say these are the values that I'm going to attempt, I now use my remainder/factor theorem, and I plug the values into my polynomial, seeking a 0. So if I plug 1 into my equation, and I don't have a graphing calculator, 2 plus 7 plus 2 plus negative 3 is going to get me nowhere near 0, right? Do I even need to calculate this? So again, I'm working more as a calculus teacher right now. All I care about is I know that doesn't equal 0. Is it actually vital for me to know what it actually calculates to? No, it's extra information. I just need to know if it's 0 or not. So basically, I know that's not 0. Okay, so I try the next one. I try the next factor of negative 1. All right, now I have to think a little bit. So that's going to be negative 2 plus 7, which is 5, minus 2 minus 3. Does that get me 0? Okay, somebody nodded yes, and you're absolutely correct. I found a factor. Now that I have a factor, I head to my synthetic division. I'll stop, go to synthetic division. I found what I needed. Pull in your coefficients, drop, multiply, add. Multiply, add, multiply, add. And if you don't get a remainder of 0, you've done something wrong somewhere. Go check your work. So now I've got a constant, an x, and an x squared term. As soon as it's a quadratic, I can probably do that with all the skills I learned in 10 and 20. So now I've got 2x squared plus 5x minus 3. Factor that however you like. And I'm going to let you do it, because I'm going to do it in the way that I was taught way back in the 80s. Yes, I'm that old. And how I do it in my head is not how I teach it. So I no longer care how you factor. You just have to be able to do it. Does anybody want to know what I was doing? Okay, so here's how I was taught. You don't have to do this, but maybe you've never gotten factoring very well. I look at the coefficient of 2 and I think it only has 2 factors, 2 and 1, correct? So that means my first bracket should have a 2 and my second bracket should have a 1, because there's the result of first. 3 only has 2 factors, 3 and 1. But I don't know if the 3 goes here or if the 3 goes here. So now I have to think. I want a 5, which means I want 2 times 3 being positive 6, and then I'll subtract my inners of negative 1. Because I did math in the 80s without a graphing calculator or without any calculator at all, my foundation of numeracy is a little different than your foundation of numeracy. I can play more in my head because I didn't use a calculator for years. So that's why I do it differently. Okay? I know this is a prime number. I know this is a prime number. That has to be 2 and 1. That has to be 3 and 1. I just have to figure out where they go. But again, I have a different foundation. So when I factor like that, I'm doing it way different. Now, when I taught you in grade 10, anybody here, Connor? I taught Connor in grade 10. I teach it differently. I give you guys a very regimented process, but I don't factor that way. All right. Therefore, hey.
I'll go here for 30 seconds.
Sure. Write the factored form of this particular polynomial, please. the integral zero theorem.
Yeah.
I discussed why we're looking at
So you're discussing potential zeros.
I'm showing how they're
Because then I'm looking at the next lesson.
Yeah.
And the next lesson.
You can do 3
all
and
of a
4 all at
sudden-
once.
Yes, it says solving and factoring polynomials.
Which is,
This.
yeah.
So I just thought this was a weird jump because we haven't mentioned potential zeros.
Factor theorem is like the
Oh,
baby step.
agreed. Now,
I can't do a whole lesson on factor theorem.
factor theorem to me is also all of the what is C and B if this is a factor and this has a remainder.
And you see, and that kind of goes with the remainder. So that, like, that's compilation.
Okay, thank you.
You're welcome, thank you. Okay. So, we got our 2x minus 1 and our x plus 3, right? But this only has 2 x's and my original polynomial had how many x's? 3. What is the factor that I used at the beginning? Well, don't forget that that gave you a factor. If I have a root of -1, that creates that last factor of x plus 1. So don't forget that those roots that we found using the factor theorem have to incorporate itself into a factor, which is why I say always do that little check. Did I write a degree 3 when I was given a degree 3? Did I write a degree 4 when I was given a degree 4? Because sometimes you lose it because we don't actually write the factor. So make sure you're checking that when you go back. Okay, guys? Did that seem okay? Not bad? All right, so factor this completely. Use the information of the intercepts to the polynomial to sketch it. All right, guys. We're going to pretend we have no graphing calculators. We don't have the graphing function. You've got a scientific calculator sitting in front of you. Pretend for now. Okay? We're not going to use the graphing function. So when I look at this, I'm like, I need to find 1, 0. I therefore look at my constant. And I say, I have potential zeros of positive -1, positive -2, positive -4, positive -8. Are we okay where I get those numbers? Those numbers are going to be my attempt to find a 0, which means I'm going to take that number, plug it into the polynomial, and hope to get a 0. Hopefully I won't have to get up to number 8. Very rarely do you have to go that far, but now I want to see, plug 1 in. 1 plus 3 minus 6 minus 8. Nope, not going to happen, right? So I'm a fan of the, I don't care what it is, but I know it's not 0. Again, a scientific calculator will allow you to calculate this. You don't need a graphing calculator for that. Okay. We move on. We try another. -1. All right, now I would go to my calculator. I would type that in, but I'm going to try and use my brain because it's fun every once in a while. So that's going to be -1 plus 3 plus 6 minus 8. Positive 9, -9. That one equals 0. Woohoo! Found it. Full stop on the factor theorem. Now I can head to synthetic division and factor that out. -1, 1, 3, -6, -8. Drop, multiply, add, multiply, add, multiply, add. And if you don't get 0, you've done a mistake somewhere. Go find it. So maybe at this stage, it's a good idea to say, all right, here's what I know. I took out a root of -1, so the first factor I knew was x plus 1. So do you see how I'm just going to kind of write what I know right now? The other factor is x squared plus 2x minus 8. Now I look at factoring that quadratic in any way, shape, or form that I can to get x plus 4 x minus 2, and now I've got that fully factored form. So sometimes it's nice to bring that factor down right away with the quadratic and then factor the quadratic. Again, your scaffolding can be what makes sense to you, but I always double check. This is a 1, 2, degree 3, feeling good. All right. What's the y-intercept of this function? That constant gives us a lot of information actually, doesn't it? That's where my potential zeros came from. That's where my y-intercept comes from. I have x-intercepts, which comes from the factored form. So I have -1, 0, -4, 0, and 2, 0. This is a degree 3 with a positive leading coefficient. So it's like a line with a positive slope, starting in quadrant 3, ending in quadrant 1. Y-intercept of -8, x-intercepts of -1, -4, and 2. We go up, down, up. Now, for our purposes, do I right now care where these ones are? Not a bit. Is that an acceptable sketch of what's happening? Guys, you just sketched your first cubic. What do you think is going to happen when it's a quartic? I'm going to use the remainders, the factor theorem, twice. Synthetic divide, twice to get to my quadratic. It's just more work, but it's the same work. Over and over and over. Okay, show that 1 is a root. Notice the change of language. But we know root is a synonym of x-intercept, 0, what are my other ones? I can't think of them anymore. Roots, solutions, fact, all of that. So if 1 is a root of the expression, that means the polynomial at 1 is equal to 0 because it's an x-intercept, a 0, or a solution. So you see how I mathematized the English? So what's the equation? What am I working with? Okay, we plug it in. Is the polynomial at 1 0? So we say the polynomial at 1 is 1 cubed minus 9 times 1 plus 20 times 1 minus 12. Why do you write this one out when I didn't write out the other ones? And I said it wasn't necessary. What's the different wording in this question that tells me I need to write it out? Show. Which means I want to see what you did. So there's a little subtle difference in the instructions that we need to pay attention to. So now I can say, all right, I can throw, oh, I didn't square that, sorry. I can throw that into my calculator. I'm going to have 1 minus 9 is -8. -8 plus 20 is 12, minus 12. But that shows my understanding. All right. Find the other factors. Well, let's factor out my root of 1 because I know it exists. Factor the quadratic that you're left with. And it's the wording. And math gets very subtle for the wording. Do I say as my answer, x is equal to 1, 2, and 6? Do I say the zeros are 1, 2, and 6? Do I leave it as it is my answer? How do I know which form they want when they're all synonyms? It says find the other factors. Did I leave them as factors? Read the instructions. I strongly encourage you guys that after you answer the question or you believe you've answered the question, read the question again, not thinking of the math. What answer do they want? How do they want me to interpret this? It's just a good little technique to have. All right, find the value of k so that if x minus 2 is a factor of that polynomial, Well, this is just what we did with the remainder theorem. There's nothing different. The only difference is when it says it's a factor, when I pull out the math, it's stating the polynomial at 2 has a remainder of 0. It's the same remainder statement, but you have to understand that if it's a factor, it has a remainder of 0. But it's the same statement. All right. We know the answer when we plug in 2 for my x's. I now simply have an equation with one unknown. Okay, 8 minus 24 is negative 16. Negative 16 minus 6 is negative 22, making that positive 22, making k 11. And I would absolutely throw that into my graphing calculator, because now I'm pretending to have one. Don't you love how I pretend to take it away, then I pretend to give it back? But I mean, on your 30-1 tests, absolutely. I would plug that in for k, graph it, look at my table of values, and make sure I got the correct answer. Factor theorem is pretty easy if you really understand the remainder theorem. How are we feeling, guys? So can we see how all of this is going to come crashing together to allow us to graph polynomials? So I always find the factor theorem is so short. I'm going to check in with you guys because we're a little ahead. Do you want to just work on the factor theorem, or would you rather me continue and then give you more time to work in class with me tomorrow after you've done some homework? Like I'm experimenting a little with you guys. I find that lesson was tiny, that I would almost like to push on, but then give you more class time after you've had time to go home and synthesize it to ask me questions. Does that work for you guys? Okay, let's give that a try. Now, this isn't anything new than what we've already done, which is why I feel comfortable moving on. It's more of the same. So, consider the polynomial. P of x is equal to x cubed minus 7x plus 6. List the integers with divide into the constant term. I would probably call these my potential zeros. But list the integers which divide into the constant term. List the factors of the constant term. Positive negative 1, positive negative 2, positive negative 3, positive negative 6. And yeah, we've seen that type of question on the diploma where it seems so simple, but you see how you're actually representing your understanding of a theorem. And that's fair game. So those questions can be as simple as list the potential zeros. It's a nice mark on a test out of 1 if you get what they're saying. List the potential factors of the polynomial. Again, it's the wording. I don't want the values of the zeros. Now I want x positive negative 1, because that's a factor. X positive negative 2. X positive negative 3. X positive negative 6. And we really want you to understand the difference between a zero and a factor. Okay, and it's where we see them and it's how we use them. Divide this polynomial by one of these potential factors to determine if it is a factor. Continue this process till 1 is found. Let's just determine a factor. I've never liked that setup because I don't want you to do synthetic division a whole bunch of times to find one. I want you to find a factor using a potential 0. Does that make more sense? Let's streamline it. Okay, so we are going to determine the polynomial at 1, and truly, I just care if it's 0 or not. So up I go. 1 minus 7 plus 6. Oh, that worked out perfectly. One try and I've got it. Complete factoring the polynomial by synthetic division or the factor theorem. No problem. Now that I've got that, I grab my coefficients, recognizing it jumped over x squared. So what do I have to make sure I put into my synthetic division? A 0 for that placeholder. So 1, 0, negative 7, 6. Got to have that column. Drop, multiply, add, multiply, add, multiply, add. Again, if you don't get 0, you've done something wrong. Stop, go fix it before you proceed. All right. So far, because I want the factors, I've got x minus 1, x squared plus x minus 6. I can now factor my quadratic to be x plus 3, x minus 2. I reread the question and I say, okay, it is saying complete the factoring of the polynomial, and those are the factors. So far, anything different than what we've done from last note? Like, this is all more of the same. Okay. Questions? Here is your first quartic. All that means is we are going to be finding not 1 potential 0, but 2 potential zeros. Oh, sorry, not potential, 2 zeros. But we start the same way. I look at 12, and in my head, or writing down because it doesn't take any time, I consider all of the potential zeros that I could be trying. I'm probably not getting up to 12, but I do need to consider all of them. So we start at the beginning. And we use our calculators, but not the graphing function right now. We will get to the graphing function, especially when I'm training you for your test. But for now, let's pretend you don't have it. We plug in 1. And I think to myself, I'm going to have negative 15, 12, 13, 14, 15. I know that's going to work. Mental math is awesome. Now, I'm not going to go and find a second one right away. I'm going to divide it out and then start the process again. So I'm going to say, because I know this is 1, let's get my polynomial down to being cubic. Drop, multiply, add, and multiply, add, multiply, add. So now I need to factor the polynomial x cubed plus 3x squared plus 4x minus 12. Notice how my constant is the same. It's still negative 12. I have the same potential zeros. So I'm going to start evaluating again. Did I do something wrong, James? Negative 4. Thank you. Like I said, I'm going to make mistakes in the simple stuff. Don't be afraid to correct me. I don't take offense. Okay, is 1 going to work? 1 plus 3 minus 4 minus 12? No, not going to work. So I move on to negative 1. So let's see here. Negative 1 plus 3 is 2. 2 plus 4 is 6, but I'm still not getting there. Feel free to use your calculators, ladies and gentlemen. You don't have to not use your calculators because I'm not. I'm having fun with mental math, trying to keep myself excited. Okay, so we move on. 2. Okay, this is going to take more brain power. So that's going to be 8 plus 3 times 4 is 12 minus 8 minus. That's looking good. Right? That one gives me 0. So now I do it again. And I take my cubic and divide out the next one. Okay, so far in my polynomial, I divided out a root of 1, creating a factor of x minus 1. I divided out a root of 2, making a factor of x minus 2. I am now left with the quadratic x squared minus 5x plus 5x plus 6. I can complete my factoring x plus 3, x plus 2. And I have fully factored my polynomial. That is how you will have to do it in calculus next quarter with Mr. Shrimpton or myself, or in university when you're not allowed to use your graphing calculators. Did it make sense? In 30-1, however, I will show you how to do it, but I need you to know the algebra. All right, guys, I'm going to need your help again. It's x to the 4. What's the next term? 2x cubed. 8x. Look good? Guys, you could graph this, and I encourage you to, and say, oh, I know a potential 0 is I know a 0 is going to be -3, -2, 1, and 2. And I can streamline that whole process by looking on my graph to get that, and to get that, and to get that, and to get that. But it's a crutch that is going to be yanked out from you. So I just first needed to make sure we could do the algebra. But if you want to say, oh, I'm just tired, I've done like 5 of these questions, I just want to go to my graphing calculator and see the 0, fine. But make sure you know how to use these theorems because they will come roaring back. Fair enough? All right. Oops. All right. Sometimes we're really, really nice to you. Sometimes we give you a question that says, solve the question algebraically. Well, if the question is already factored and it's equal to 0, the solutions simply come from the factors. So once it's factored, the solution will come from the factor. Will give it to me. Is everybody okay where I get 5 halves? Sometimes I'll come across somebody who doesn't know what I did there. Are we okay? Okay. Next one is +7. Next one is -1/3. And if you have the factored form, you've got the solutions. But if you don't have the factored form, now you're going to have to figure out the solutions. So again, I default to a little bit of algebra, but why don't we play with our calculators since we're kind of doing 2 lessons at once? So if I was tired or this was a test, I would say, okay, you know what? I've had enough. Let's just go x cubed minus 19x plus 30. And let's take a look. Okay. I am pretty positive that I am going to have a root at 2. Let's check. Trace to enter. Make sure you get that 0 there. Because could it be a little bit off, but you don't see it because of your graphing calculator? So just take a second and double check it. So I know 2 is going to work. So if I want to show my algebra, I can jump to there. I've now used the factor theorem. I've now proved that that's a factor, and I can go ahead and jump into my long division. Drop, multiply, add, multiply, add, multiply, add. I can now state that my polynomial is x minus 2, x squared plus 2x minus 15, x minus 2, x plus 5, x minus 3. The solutions are therefore -5, 2, 3. Good algebra? If this was a multiple choice question, could you read the answers off the x-intercepts? Again, I'm just making sure you've got that algebraic base so that you can be successful. But if this was a multiple choice question or a numerical response question, I'm going to the graph and I'm reading it. No doubt. Okay? So don't be afraid to, but these will get taken away. Okay. Oh my gosh, it's a cubic. Give it a try. Use your crutch. I mean, 36 has an awful lot of potential zeros. I would encourage you to graph it, grab a 0, and then please show me the algebra, please. I need to know that you're getting this. So if you're using your crutch, please notice this one only has one of the solutions, which is an integer. And we do that on purpose sometimes so that we can make sure we see your work. Now, if I want the solutions like this question, I could still read it, but I want you guys to practice the factoring. Verify it's at 4. And start go. Yes, if this was a multiple choice question, I would have just read the answers off. But we're making sure we get algebra. We're making sure we understand the process, but we can verify. Now, here's an interesting side for some of you. Let's say we knew the answers and we decimalized them because we're ridiculous. And I say, write for me the factored form. And you've just always gone to your graphing calculator and got the answers. You're like, I don't believe you, Mrs. Rawlik. That's ridiculous. Why would I do all that work? That's stupid. And you did this. Are you right? Is that the factored form of that polynomial? And the answer is no. Straight off, no. You're totally wrong. Okay, there's being lazy, then there's being way too lazy. And the reason is, if I distribute this, I'm going to create an x cubed. My polynomial wants a 4x cubed. So if you get too lazy and just always read the roots off and just always put them in, doesn't always work. That is not the factored form of this. And it's that leading coefficient that you're missing when you don't do the proper factoring. So careful with when you decide to take shortcuts, right? They don't always work. You think they do until they don't, and then you really struggle because you didn't bother to learn the proper way to do it, right? So shortcuts can bite you in the butt. That is incorrect. And if you foiled it out, you would see why. Make sense? There's being lazy, then there's being too lazy. And then you're wrong. Okay, solve the equation using a graphing calculator. So when you get this statement, I don't want to see anything but the answers. So that would be like a multiple choice question. That would be like a numerical response question. I would just go straight to my graphing calculator because those are the instructions. 1 to negative 13. 1, 2, oh, I forgot the 2. 2. Ugh. Getting old sucks. 1, 2, negative 13, negative 14, and 24. Now, if it says using your graphing calculator, they truly just want you to go grab them. I believe there is one at negative 4, negative 2, 1, and 3. I would definitely, though, make sure it's not slightly off. So I would go, okay, that's negative 4, good. Negative 2, good. 1, good. 3, good. 30 seconds can save you a problem, correct? So if it says just do it with your graphing calculator, there is literally no work. It would be a 1-mark question. Staying with the graphing calculator, find the zeros to the nearest hundredth. Okay. 1, negative 3, negative 3, 1. Let me put that one in. 1, negative 3, 3, and 1. So again, we're just making sure you can hit the buttons. Teachers will teach you differently. You do how it makes sense to you, but know that in your trace menu, you're either finding a 0, or if you're doing the Chandler method, you put y is equal to 0 and you're finding intersects. I don't care how you do it, truly. I like left and right because I just literally type in numbers. So I hate the guess. Negative 1. Well, that doesn't eat it to the nearest hundredth, so I'm feeling good about that. 0, somewhere between 0 and 3. Okay, there's my nearest hundredth, 0.27. And last but not least, somewhere between 3 and 9 is 3.73. And we just want to make sure that you can find them. You should have these skills, but we find if we don't review, there's somebody who is like, I've never used a graphing calculator. It's amazing. Okay, what's the difference between factoring and solving? Factors look like this. Solving looks like this. So that's why I say be really careful and read what you're being asked. Do I want the factor form or do I want the solution form? So the solution is an interpretation of the factor. I think we're pretty much done. Yeah, okay. But you know what? Why don't we do the same thing we did last time? Nothing was really new, but these will be good questions to start with. Like, did you guys like that, how I kind of gave you a little bit to do and it wasn't too hard? Then when you came and you were with me again and you had that knowledge, then we did the harder stuff? Let's try that again. So let me take a look at your homework. So I don't want you to do too far on this. I'd rather you do that in class with me. So I'm looking at page 134. Let's see where we get too hard. So we've got number 6, factor fully. Number 7, determine values of K. You can do that. 16A, factor. You can do that. Page 147. Number 1 and number 2. Oh gosh, you can do all that. They're all factor questions. So none of them are hard. Okay, but let's stop here. And that way that'll give us a good chance to kind of dive into something tomorrow to make sure everybody gets it. Sound good? Fantastic, ladies and gentlemen.